Atomic particle structure, Threads and Spinons Theory. Core principles. Threads. Atomic particles are made of one continuous thread. This thread folds and twists to create the structures we observe as protons, neutrons, and electrons. The thread is under tension, creating the forces that bind particles together. Spinons. Spinons are rotating elements along the thread, responsible for energy transfer and interaction. Spinons' rotation defines particle properties like charge, mass, and spin. Charge. Charge arises from the rotational direction and alignment of spinons within threads. Positive charge. Spinons rotate in a coordinated pattern aligning outward. Negative charge. Spinons rotate in the opposite direction. Mass. Mass is the result of thread density and spinon activity within the structure of the particle. Proton and neutron structures. Proton, a tightly wound thread structure with spinons spinning predominantly in a unified direction. Neutron, similar to a proton but with partially offset spinon spins, balancing out charge. Electron structure. Electron, a more loosely bound thread with spinons spinning in the opposite direction of protons. Mathematical framework for particles' thread tension formula. Mass density relation. Charge distribution. Spinon energy formula. Particle stability condition. Binding forces and atomic nucleus thread tension bond formula. Nuclear stability formula. Thread spin and waveform predicted by tension oscillations. Thread spine and waveform. Conclusion. The Threads and Spinons theory presents a revolutionary framework for understanding atomic particles and the forces that govern their behavior. By redefining particles as configurations of a single continuous thread energized by rotating spinons, the theory offers a unified model that connects quantum mechanics to macroscopic phenomena. This approach eliminates the need for traditional notions of discrete particles, instead emphasizing the dynamic interplay of thread tension, curvature, and spinon rotation. The mathematical framework supports this paradigm, providing equations that describe mass, charge, energy, and particle stability in terms of thread properties and spinon dynamics. Key predictions, such as the role of thread tension in binding forces and the oscillatory nature of threads, align with observable phenomena, offering a path for experimental validation. These formulas also extend to nuclear stability and particle interactions, laying the groundwork for reinterpreting molecular bonding, atomic structure, and even gravitational forces. This model challenges conventional theories, including string theory and the Standard Model, by proposing a simpler, testable alternative that relies on three physical dimensions without invoking additional, unobservable dimensions or exotic constructs. The inclusion of the Spinon Energy Unit, SEU, as a universal measure provides a consistent tool for quantifying energy across scales. In conclusion, the Threads and Spinons theory is a transformative framework with the potential to unify physics from quantum scales to cosmological dynamics. Its mathematical rigor and testable predictions mark a significant step toward understanding the fundamental nature of matter and energy, inspiring new directions for research and experimental exploration. This model not only reshapes our view of atomic particles, but also offers profound implications for the interconnectedness of the universe.